Right. Excellent. Welcome back. So thank you, Matt, for a great introduction into how this works and the first few initial important concepts. So now, uh, right, I'm going to make these actually hopefully visible. Well, it's marginally visible, I hope, but you should also have this notebook that you can follow along through as I go. Feel free to stop me at any time if you have any questions about this, right? Okay. So in this lesson, we're going to actually start looking at data that's on disk and making data containers that allow us to actually query data and get it and start doing interesting things with this, right? So we'll talk about geometric data containers, which are not the only data containers that YT uses. We'll talk about how to get the field data. We'll talk about the type of the way that that data comes back to you, which are called unit arrays. And we'll talk about a few other things, field aliases and how to make profiles. Okay. All right. So just to review, what were a couple key concepts, right, that I will refer back to? Number one was the data set, right? So we loaded these things and we had the shortcut DS typically for data set, right? So a data set essentially here, because data sets can mean a lot of different things. In YT verbiage, a data set is essentially a collection of data that we load all at once with something like yt.load or yt.load sample. And as Matt pointed out, this is a cheap operation that should happen really fast, and it just holds some useful metadata. It is an important operation if you want to sift through data sets. You should be able to load them over and over quickly to find exactly what you're looking for. And you should expect that to be cheap and fast. Secondly, is the front end, right? So the front end is essentially how we define one distinct source of data. Does it come from an ENSO simulation, a Gizmo simulation? Is it a satellite image, a CT scan, so on and so forth? So the front ends define the different places that the data comes from, and they give us this index object that Matt has run through, which is this fairly complex thing under the hood that is determining the relationship between the files on disk and the actual physical representation of the data, right? We haven't actually accessed any actual data other than this metadata, okay? So now I'm going to introduce two new concepts, right? One is a field, right? And the field is essentially a word that I will be using sort of synonymous with the data, right? So a field is an array of values describing a quantity associated with each element in the data set. This is the data we want. So if I have astrophysical simulation, this is all of the gas densities or all of the particle masses or positions, right? If this is an image, it's all of the bands in each pixel, something like that. These are the fields, okay? And then a data container, also referred to as a data object, is an object that contains one or more elements, right? So when I say an element, if I'm talking about a simulation, this may be a grid cell or a particle. If I'm talking about an image, this may be a pixel, right? The thing that the data set represents multiple, right? So the data containers provide access to the fields for all the elements that they contain or are associated with or are defined by, right? So I'm going to use one specific data set from the workshop collection, which is in this primordial star folder. And there are 4 or 5 data sets in there. I'm going to use the last one, which is DD0157. But if you have other data that you can load with YT data, you can use that as well, right? So I'm going to begin with the two things that we always start with, importing and loading, right? So I've loaded one data set, and here we can see we have a bunch of this metadata, the time that the snapshot represented, some things about the domain size, and some metadata associated with the cosmological parameters associated with this cosmological data set, right? Okay. So there are many types of fields available, and I'm going to start with the most basic ones, right? The data that was saved on disk by your simulation or your image, just the raw stuff and the names that we associated with it, right? So these are going to have names that are specific to your front end, the place that they came from. So they may have, camel case naming convention. They may have shortened names, right? They may be little, keywords or nicknames, things, right? The first thing we want to know when we open data, especially we've never seen it before, one of the things that I think YT enables is for us to open and look at data that we have never seen. That's something that I really like about this, right? So the field list, as Matt discussed before, is going to tell us what is available in this data set, right? So the next thing I'm going to do is I'm going to run ds.field_list. Okay. And that did this. And now notice, so that returned, it did this parsing of the hierarchy, and then it returned this list of tuples of names like all and particle mass or ENSO. So this is an ENSO data set, cooling time, DII density, so on and so forth, temperature, total energy. So here we have like a combination of naming conventions with camel case and underscores and hyphens even, right? But this is how the people who wrote ENSO made their choices, right? This is the niche of that front end, okay? So the field naming conventions, this is something that we should discuss here, right? So when you access field data in ENSO, you do it by its name, right? And all fields in ENSO are named with a 2-element tuple of essentially of type and name, right? Now, a couple notes about creating the field list. Notice that this wasn't completely instantaneous, as Matt has pointed out, right? So loading the data set was effectively instantaneous, but getting the field list is essentially the first expensive operation we've done. And the field list itself is not really the expensive part, but it has built this index object the moment we've asked for fields. Why has it done this? Well, because for many data sets, we allow the data set to tell us what's there rather than pre-describing these fields are associated with this type of data. So for ENSO, for example, what we do is we actually open up some of the file. They're HDF files. We look for the names in there and we say, that's what it is. So that's why that takes, a blink of an eye as opposed to shorter than a blink of an eye, right? Okay, so that's what's happening here, all right? And these field names are mostly defined by the front end, okay? So now that's just going to tell us the names, but we may want to know a bit more about what they are. So we can use this thing called field info, right? Field info is another another attribute hanging off of the data set object that we have loaded. And we can query field info essentially like a dictionary, and it will return to us some information about these fields. So let's do that. I'm going to do this one called density. And all it's going to tell me is a few things. It's going to tell me that it's an on-disk field, right? And later, we're going to distinguish between the fields that are just there and things we call derived fields, which can be so much more, right? Products of all of these things, right? So it's telling us that ENSO density is an on-disk field, but it's also nicely giving us some units, right? It's giving us units of code mass divided by code length cubed, right? So that is a unit of a mass density, but in some sort of internal unit system that we haven't really discussed, right? But as you know, most simulation data, at least, is not run in MKS or CGS or anything like that, because those, a combination of those units and astrophysical scales give you numbers that don't play well with computers because they're very large. So we have these internal unit systems. So when we write things out, they tend to be in these unit systems that don't make a ton of immediate sense, but they help the simulation. So let's look at a few of the others, right? There's X velocity. It has units of code velocity. There's gas energy, which has units of code velocity squared, right? Because this is essentially a specific energy. Now here's a particle one. Right, so this is a particle mass. It has units of code mass, but it also tells us that it is a particle field, right? So ENSO is a grid mesh type of data, but it also has particles that can move around in it. So we can load multiple types of data with one data set, right? So an even better way to get information about this is by using this thing ds.fields, all right? And the nice part about ds.fields is essentially the convention in which you use it is ds.fields dot field type dot field name. And what this allows you to do is use the power of the dir command in Python to discover what's here, right? So you can do dir on ds.fields to see all the available field types that have come into existence when we have loaded this data. And you can do dir on ds.field dot some field type to see all the fields that are in existence for that type, right? And so when I do something just like ds.fields dot n-body particle mass, I'm just going to get the same information had I queried ds.field info n-body comma particle mass. But you can try this dir thing and see what you might get for that. Or if you have, I don't know what you need enabled to do this, but if you have, you can type display ds.fields and it will bring up a nice little drop-down widget where you can search in them. That's going to give you a lot more information than I want to cover, but you can try it. It doesn't work in the sort of slideshow mode. This is why I've commented it out here. But you can try doing that. Has anyone tried it? Yeah. Do you get like a nice little widget?
Yeah, I'm not sure what the source code is representative of, but I'm gonna look like I've not really looked at it yet.
Right. Okay, so this is going to reveal more fields,
Yeah.
fields that are combinations of other things, and you can actually see the code
Yeah,
that's written to do
yeah,
that.
it looks cool.
So you can do far more than I want you to know about now, but it's all there for you. Okay. All right. So now we know what data we can ask for, but now let's actually get some, right? So now we need data containers, right? These are the things that provide access to the data. This is the way that we access all of the data in the simulation. And by data, I mean the field data, right? There is a link here to all of the available data containers, right? So this is the documentation. I'll try to do this throughout this presentation to provide links to data. But for now, we're going to start with the most basic one. And frankly, the one that I think is one of the most empowering, right? Geometric data containers, right? Because when I am thinking about my simulation, I am thinking about the shapes of things in it, right? A dark matter halo is spherical or it's ellipsoidal. The filaments are, a series of cylinders or stacked, right? Like this is how I describe the data. This is how I ask for a chunk of data from a piece of it, right? So we have shapes representative in dimensions of 0, 1, 2, and 3D, right? For 3D shapes, they provide access to all the elements. And by elements, I mean the grid cells, the particles, everything that would be contained inside their geometries, right? For 3D data, right? And for grid cells that have like a fixed volume, essentially, it's if the cell center is contained within it, not if it's wholly contained, just the cell center. Okay. Then we have shapes of lesser dimensions. All right. And I'll talk about what they are. And essentially, what you get from a shape with a lesser dimension is if that shape intersects with the data itself. So if it intersects with a grid cell, or if it's a particle and it has some sort of kernel associated with it, if that shape intersects that kernel. And I'll make it clear what that means quite soon. All right. So here are some examples of some 3D data containers that are supported in the code. Right. We can do a sphere. We can do a disk or a cylinder. Right. A sphere, we simply define with a center and a radius. A disk requires two more things. We have a center, we have a radius, but we also have a normal vector, which is the orientation, and then we have a height, right? We have an ellipsoid, which is fairly complicatedly expressed. And then we have this shortcut called all data, if I just literally want all the data, right? I hope that frequently you won't want that, right? Because what this kind of way of doing things allows us to think about data that is gigabytes and gigabytes and gigabytes in size. Situations where we never want all the data, right? Or that most computers probably aren't going to be able to handle, right? So here is what I'm talking about when I said shapes of lesser dimensionality, right? So in 0D, I'm talking about a point, right? Like one point in space, one XYZ coordinate, right? And if I make a point and then I ask for the data, it will be the data that that point lies inside of, for example, like if it's a grid cell or if it's a particle, if it's inside of a kernel, something like that. Array is a 1D line with a start and an end point, and all the elements along that array that are intersected by that ray, we will get those back, right? And then we have a cutting plane. We also refer to this as a slice, right? This is essentially a plane, right? Any plane, it does not have to be aligned with the axes. It can be at any orientation whatsoever, and we will get all the elements along that. This is just a few of the main geometric data containers out there. But Corentin will cover later many other non-geometric data containers. You can see there's a lot of other ways to get data out of this. But this, I think, is one of the most powerful, simply because I think this is generally how we are trying to think about what's happening in the data, if you ask me, right? So let's start creating some data containers, all right? I'm going to do mostly with spheres because they're simple, but you can look up the syntax for how to make some of the other data containers, and you can try those as we go along here, all right? So a sphere, as I said, represented simply by a center and a radius. So I'm going to start very simply with things that are not really informed by all that much, okay? So if you remember when we loaded this data, we had all this metadata that came with it, right? That immediately kind of printed a bunch of this, right? All of that metadata is available to you as attributes that are hanging off of the DS, the dataset object that you have loaded. So you can see, for example, here, we have the domain center and we have the domain width, right? So we can make some fairly uninformed choices that are at least not unreasonable to just start getting some data. So I'm going to center a sphere.
With the vector.
What's that?
With vector center.
The domain width is a vector.
Document 0. Yeah.
Because it's 3D in size, right? It's the domain, right? So in fact, maybe we'll just print that off in a second, but right. So let's do that. And actually, if you want to, you can do ds.domain width and see what you get out, but it is the XYZ size of our 3D volume, right? Okay. So I'm just going to do a simple thing, center of the box and 1/10 of the size of the box for a radius. Just want to grab some data, and I don't really care what it is yet. Okay.
We have,
Yes.
oh, not to well, actually, we also have units that are scaled to the domain width as well, that we'll probably talk about a little bit later.
That's right. So make this object. I've made a sphere. I've made a data container, and this operation is cheap, all right? We can make as many of these all day long as we want, right? Because we have basically done nothing other than say, I want it here. Now it's popped into being, but it hasn't asked for any data yet. Okay. Now we finally get to access data, right? So these objects essentially act like Python dictionaries, right? And when you want data, you query your data container object that you've made like a dictionary using the field names that we have already shown you, right? So the on-disk fields that came out when we did ds.fieldList. So let's do that. And I'm not going to like capture this, I'm just going to shoot it right out. So I've queried that, and what have I gotten back? I've gotten back a bunch of numbers, right? So I've gotten back the on-field densities for all of the grid cells contained within this sphere at this fairly uninformed center and radius position, right? So all these values, there are 10,227,003 of them, and they have the same units as we saw when we did field info, right? Code mass per length cubed. All right, so what is this that we just got back? What is returned from a data query? All right, what is returned is something called a unit array. And a unit array is essentially a slightly fancier NumPy array. If you've used NumPy arrays, this is a NumPy array. The only difference is that we have these symbolic units attached to them, which are great because then we can also convert to whatever we want, provided it's in the same dimensionality, right? So that's thing one. So I can do that quite easily with the .2, right? And then I specify the units as a string using Python syntax for multiplication, division, and for exponents, right? So let's do that. Right. And now I'm getting back numbers that if you're an astronomer start to make sense in grams per centimeter, which many will tell you is a terrible unit system. Thankfully, John Peacock is not here. But we can see these numbers start to look like that, right? Do it. Yeah.
Suppose someone has stupidly not included units. How do we give it the right units?
Okay, so I think right now the answer is that for data or for front ends where that's not necessarily baked in, it's defined in the front end in YT, but there are ways to turn things into unit arrays, right? I'll show that in just a minute, right? So
Because they would be like unitless. They would say dimensionless. But
Right.
they're not.
right, yeah.
You can often specify it in the load command. So we haven't done a lot with this yet. But in the load command, there are a number of different things you can specify, including like if your axes are in a different order.
Right.
If it's ordered ZYX, or you can specify the geometry, and then the unit system is often fully flexibly specified there.
I see.
Which I think insane. I'm sorry.
No, that's fine.
Totally.
That's fine. Yes, but we don't have a great way yet of saying, here's data that's unknown and what its units will be. And I think, to me, this is something that I would like to accomplish this week, is making that happen.
That would be actually
Yeah.
useful.
So we can do that with other things like solar masses. So this unit package knows about quite a few units. It knows about prefixes, kilometers, centimeters, things like that. Right.
Suffixes, CM.
Right, and CM and co-moving suffix for cosmologists out there, right? And it also does nice arithmetic operations. So I'm going to multiply density by temperature, and it can, number one, it can do that because it's just NumPy arrays. But number two, it has applied a consistent unit system. In this case, I'm going to leave it as something slightly nonsensical, but it has done it, right? It is now kelvins times code mass divided by code length cubed, right? And you can do this, you can smash them together as many times as you want, and you can also reduce them. We'll do that later. All right. Now here's another thing, right? So another point to be made about this is when I query things, they're coming out in a specific order, right? Not necessarily an order that makes intuitive sense, but it's always going to be the same order, such that when I multiply density by temperature, I know that the first value in the density array is also the first value in the temperature array. They are the same element, right? So whenever we query data in this way, you can do these operations because we are grabbing it in the same order from the data container. That's a key point that allows this not only to have consistent units, but to make sense, right? That always happens. That always works, right? Now, here's another thing. that'll happen. So I queried density before, and if you were really watching the screen, you notice it took, you know, a blink of an eye, maybe a tenth of a second, right? But this next time I do it, it's instantaneous, right? So when we query data from a data container, it is cached. It is saved in the data container until we either throw that data container away, we delete it, or we call this clear data on it. So I'm going to do this again. I'm going to clear data and I'm going to immediately query it. And we should see, right, it took that like fraction of a second again because we deleted it. Then when we asked for it again, it had to get it from disk, right? But YT is smart enough to figure out what it's already got and what it needs to get, and it will do all of that for you. Okay. The other thing that we can get, this is technically not an on-disk field, but I want to cover it here, right? Is the spatial information. This may be baked into the data. If you have particles, that's something you explicitly need to write out. But for grid cells, you don't necessarily, right? You may just write the corners of the grid. It may be baked into, you know, some naming or numbering convention for it, but we can always get them through this index field type and then specifying the XYZ, right? That will give us the positions. And we can do coordinate transformations. So we can transform to spherical and cylindrical, and then instead of XYZ, we have spherical radius theta or pi, or phi, sorry, and cylindrical radius theta or z. All right, so I can just do something like that. Right. Now I'm getting a radius. Now technically, the radius also has some implicit thing in it, which is that we needed to know a center, right? So that is baked into this data container and other data containers. The other useful bits of information that we need for spherical, we just need that center, right? But, you know, for cylindrical, we need center and we need some sort of implicit normal vector. For things like disks, that's expressed explicitly. For things like spheres, it's assumed if no information is given, but there are ways to get it. Okay?
Could you explain spherical radius, the results? What are the triplets?
They are single values. This array has the same shape as that one. It's a 1D array.
Oh, I see.
Yeah, the same shape. Okay. So I'll run through this quickly. Ray data containers are also very useful. They allow you to make things like quasar sightlines through your box. Or if you just want to know what's the data contained along some vector. So for array, I just specify the left and the right, or the start and the end corner. I will lazily choose the left and the right corner of the domain. And then we can query them in the same way, that's fine. Get values back. And the rest. Okay. And then we get a couple other special things. We get one called DTs. Come on back. There it is, right? And this is essentially the normalized length of the array segment through that element. So the length of this element through the grid cell. All of these will add up to 1. Now, here's one little caveat about this. We also have this field called T, which is essentially the accumulated DTs as you go along. And the final one should be just 1 DT short of 1, right? Except they're not done in order, right? So if I query that ray T, you're going to see values that come all over the place because they've just been pulled from the data. All the calculations have been done right, but we haven't bothered to sort it for you. But you can do that sort with a simple NumPy arg sort. That'll give you the sorting order. And then when you ask for something else, you'll get it sorted along that line of sight. So like this. Right. Now, when I query this T, it didn't show before, it goes monotonically from 0 to 1. A little bit more on unitful arrays. Don't want to run too far behind. So the generic thing that is this array with units is something called a unit array from this package called unit, UNYT, because we made it. Right? But you can use this independently of YT. You can pip install it, const install it, whatever. And the two main things that it comes with, apart from many other things, are the unit array and the unit quantity. Underneath, everything that you've been getting back is a unit array. If you have a single value that you want to think of as an array, that's a unit quantity. That's all the real differences. Okay, so I can import those and I can make them generically like this, right? You can have a single value, you can have an array in here, and then you simply give it the units. You say, I have this array, np.arrange 10, whatever, but I all want it to be in kilograms. I have some quantity that I want to be in kilometers per hour squared, right? And then I can do all the things as we did before, like multiply them together, and then I can convert them into a completely different unit system. As long as it's dimensionally correct, it's going to work. Kilograms multiplied by units of length per time squared, it's going to give me a force. And I can say, pretend that force is newtons, and there you go. So this you can do any day of the week without using YT at all. And to convert, we use this .2. So if I have my array, I do .2, that will return me a copy of the array in this converted units. The original array is still in the old units, kilograms. The .convert to units will convert in place. So when I call that, and then I again query this array, now that's been changed. All right, so you can change in place, or you can do this, and this makes a copy. That's the one thing to know, right? If you're really caring about memory. Yeah.
Yeah, would it be because I learned about deep and shallow copies recently after messing up some data. What kind of copy is it?
What do you want to say about that?
So there are multiple things in that question. One of them is that it is a shallow copy of the array. There are strange situations in which the depth of the copy of the unit registry is important. And that comes up if you're comparing. So in short, it'll be the array data actually gets copied in this case. The unit registry does not. So it's a deep copy of the array, shallow copy of the unit registry. And that should only be a big deal in cases where you're either intentionally trying to do something like trying to mess with it, which there are good reasons to do that, or when you're comparing across different redshifts. And the reason that it matters with across different redshifts is because the unit registry tracks co-moving information as well. Right. And so like it is possible to find situations where like addition, if I'm remembering correctly, where addition is not commutative based on adding across different redshifts because the co-moving value, like you can get into that situation. So the unit registry, shallow, array, deep.
I should say the unit registry is essentially like the dictionary under the hood that has the conversions, right?
Okay.
So one thing I haven't discussed, which I think I do have a note about, is that if the data is cosmological, we have co-moving conversions, right? But as you know, the co-moving to proper conversion changes with time. Right? So you have to be careful about that. Right. So
I never use two. This is all very alien to me. I always do convert to units to make a copy.
Oh, all right, enough.
Yeah.
Anyway,
Or in units.
So here's the one thing to be aware of though, right? So this isn't going to work. SumArray.to code mass. You can try it. It's going to give you an error, right? Because this array was created generically from unit and it has no knowledge of what code mass is. Code mass came from the data set that I loaded. Two separate things that have not talked to each other. All right, so that's not going to work. But that's why we have we have these like helper functions hanging off the DS that are ds.arr and ds.quan. They do the same thing that I just showed you, but with the data set's knowledge of the unit conversions. So here now I can say something like that, right? So if I say ds.r on this in kilograms, then I can convert that to code mass, right? So there are ways of making generic arrays that also know about your data's unit conversions. That's the point here, okay? In cosmology, we have this proper and co-moving reference frames, right? And if you want things to be in co-moving, you append this CM to the back of your units. That's the best way we could come up to do it. You may think, well, why didn't I just put it at the beginning? Because that looks like centimeters, right? So we have to be very careful. So we have,
Like centimeters.
yeah, we have MP, yeah, I know. Well, we have MPC co-moving, MPC, and then we also have H, right? So if your simulation had a value for the Hubble parameter.
Mention in all literature to put a little c in front of a capital M for.
Yeah, except then that would be a centi-megaparsec.
Which we also special case the
Yeah,
capital M
already.
for MPC.
Yeah.
Because we want to, or we, for the lowercase m for MPC, because milliparsec is not a useful thing, but people often use lowercase m for.
We have to be,
Special case a couple things specifically with respect to megaparsecs and
I
cosmology.
think we have to be generic beyond cosmology, that cosmology's conventions have to take a little bit of a backseat. Right. So we could do that. Yeah, so here is my 30-second version of what Matt said about loading two data sets that have different moving to proper conversions. You know, a data set at redshift 0 and a data set at redshift 1. They will convert those differently. So you have to be extremely careful about that. If you want sizes, for example, or radii, you know, a co-moving, a proper radius at one will not be a proper radius at the other. Multiplying them together could be dangerous. But if you just want to know positions, there is an absolute way that I recommend, which is this unit system that Matt referred to earlier called unitary. Unitary is defined at load time as normalized to the size of the box, or at least one of the dimensions of the size of the box, right? And this is always going to be from 0 to 1. And this will always give you a consistent value between multiple loaded data sets, right? So if you want to know that particle that was there in data set 1, is it also there in the same place in data set 2, refer to it in unitary, and you're going to get a consistent answer, okay? Now, I'll quickly say we have some way of sort of converting all these different ways of describing mass and density with a capital D or a lowercase d or whatever with these things called field aliases, right? So since YT, for example, loads, you know, 24 different astrophysical simulation types, but they all have gas densities in them largely, we define these field aliases like gas that we can then refer to with a consistent naming convention. So that consistent naming convention is lowercase and underscore. So now I can query that and get the gas density, the same values before, but in a predefined unit system where, for example, we're always going to do it in CGS, right? You can convert it back to code mass per length cubed if you want to, right? But you don't have to, right? There are the field aliases will also cover other derived fields like pressure and things that don't necessarily exist on this. Okay. There are also a bunch of useful helper functions that I think this is probably the best place to stick them in for making informed decisions about where to make spheres or, you know, where to center data, so on and so forth. Like, and these hang off of not data containers, but they hang off the data set. So find max, find min, field values at point, field values at points. I think they're fairly self-explanatory, right? But I'm going to do ds at find max on gas density. Takes a minute because it actually has to comb through all the data. That's the thing you got to be careful about with these, right? You have giant data, you're asking for the one thing or the few things in the giant data, right? So don't be mad when that takes a while. You've asked for something that takes the whole data set, right? So here it is. There's the value, 10 to the minus 10 grams per cubic centimeter at that point. And now we can use that, for example, to make a much better sphere that is actually informed by what's going on in this data, right? So now I'm going to use that ds that find max. I'm going to take that center position, oops, and I'm going to make a new sphere at that center with a radius that I used earlier. Okay. So now we're going to talk about something different. This is the last thing we're going to talk about here. This also doesn't necessarily stick into data containers, but it's one of the most common things that you might want to do with data, right? Is essentially to bin it in different ways and get multidimensional histograms of the data, right? So that's what we call profiles, right? Right. And we have canned plotting methods for plotting 1D and 2D profiles, but this create profile function will work all the way up to 3D binning fields, right? And then you can get another field as a function of those bins of those 1, 2, or 3D fields, okay? And that's what we're going to do here, right? So I'm going to start with a 1D profile. I'm going to get density as a function of radius. That's what I want, right? And when I do these with something called a weight field, what I'm going to get is the weighted average of the profile field in the bin fields. And if I have no weight, I'm going to add up the values in it. It's going to be basically a true histogram, right? So I'll run this, and I'll run it on that data set, or on that sphere that I just created, right? And now I'm going to actually plot something, but I'm not going to use YT's plot yet. Those will come up this afternoon. I'm just going to do it with Matplotlib. All right. And I'll do a log of this profile. Oops. Come on back. There it is, right? So there's my average density as a function of radius for this sphere. Right? Looks pretty good. And I can use this to make a better choice, a more informed choice about the radius, for example. Look at that sphere. Or I can look at this profile and say, I really only want data that's, 10 to the minus 21 grams per cc and up, or something, 10 to the minus 22. So I'm going to make the sphere 5 proper parsecs in size, make a new sphere, right? You can use different arguments for data containers. You can use a unit or quantity or array, right? You can use a tuple of value and string for units. You can specify floats or arrays without units, and then an assumption will be made about what they are. Usually that's code length, right? We'll go through this a little quickly. We're nearly out of time here, right? So I'm going to make this profile again, all right? Show it. Now I've made one with a weight field again. Average temperature, function of density. What else do you get out of this, right? You get a few things, all right? You don't just get, if you do a weighted profile, you don't just get the mean values, you get the standard deviations as well. We get them for free as we do this. So for example, I can use this fill between to actually show standard deviation on that too, right? We get a couple other things out of a profile object. So when we create profile, we get this profile object back. We get this .used attribute, which actually is the shape of the profile, and it tells us which bins had any data. So it's a Boolean array, and we can use it to filter out bins that had no data, so we don't get plots that just sort of jump up and down, right? They're all true in this case. It is just that great, right? We get profile.x, which is the bins. It's actually the bin centers. And then we also get profile.x bins, which is one more. It has the left and the right edge, right? And if we have a two-dimensional array, we get .y and .y bins as well. So this is just for your use. You plot with dot X because that's the bin centers, but you have your edges as well, right? 2D profiles, very similar thing. Now I'm going to specify two binning fields, density and temperature, and then I want to add up the mass in bins of density and temperature. So this is an unweighted profile. So I'll say weight field none. Oops. Plot it. Now I get something a little bit different. So I'm plotting this with P color mesh. Yeah. Now I get the amount of mass in these bins. Okay. So this is sort of where we end. I've given you a brief overview of what you can do here, but what else can you do with geometric data containers? For example, you can combine them, and I don't know if I'm stealing your thunder on this or not. Okay, well, I sincerely apologize because I'm not going to do anything with it, so you will. You can combine them together, right? The circumgalactic medium, maybe to first order, is a halo with the disk cut out, right? And you can do that by subtracting the sphere, the disk from the sphere, right? You can do and or, and exclusive or, subtraction, right? You can build your complex structure that represents your physical system from logical operations on these ships. So there's so much more that you can do with them. And this is really like the first step, right? So we're going to stop there, and then we'll move on to one more about another thing we can do with data containers, and then we'll have one.